So we have proved that suppose you take an ideal in a ring R, then you can show that R by I will form a ring which is called quotient ring of R modulo I. Okay. Okay. Now let us have a look on an example that okay. Now let us have a look on the observation we can have is that suppose I be an ideal in R, then you can define a map phi from R to R by I by the rule that is phi of A goes to A plus I. Then eventually this map will going to be, the fact is that it will be a homomorphism. It is a ring homomorphism. As because you can check on your own that phi of A plus B will be A plus B plus I, which is equal to A plus I plus B plus I using coset addition, that is it is phi A plus phi B, and if you take the product then it will be AB plus I, which is going to be the A plus I product of two cosets A plus I and B plus I, that is phi A phi B. So it is a ring homomorphism, and not only that, by definition this phi is onto. So therefore this phi is an epimorphism. From R onto the quotient ring R by I, and this is called the canonical homomorphism. Okay. Whenever you are considering an ideal in a ring, then you can define a canonical homomorphism from R to the quotient ring R by I. Okay, and here you can deduce that the kernel of that canonical homomorphism is actually the ideal I. Okay. Now let us take the reverse one, that is suppose you take R be a ring and you take another ring R dash be another ring. Okay, then we can prove that each homomorphic image of R must be a quotient of R modulo some ideal of R. Okay, which is evident from our next theorem, which is called the first isomorphism theorem. For rings, we have already deduced a first isomorphism theorem for groups, and certainly the statement for groups was that if you take a group homomorphism from a group G onto another group G dashed, then the conclusion is that G by kernel of F is going to be isomorphic to G dashed. In a similar way, for rings also, if you take, suppose you take a ring homomorphism F from a ring R to R dashed, be a ring homomorphism from R onto R dashed, then our conclusion is that this R by, if you take the quotient with respect to its kernel, then this is isomorphic to R dashed. Okay. So what is the proof? The scheme of the proof is same as that we have witnessed in the proof of the theorem in groups. The same thing will happen, because suppose you take this ring R and this R dash. So here you have defined a map, a ring homomorphism F. Now already from the above observation you can define a canonical homomorphism from R to the quotient ring R by kernel of F. Suppose you take this as psi. Then with respect to this psi and F, you can define a map from R by kernel of F to R dashed, which is, suppose it is phi. Okay. Then we are defining this phi in such a way such that phi compose psi is going to be F. That is, this diagram will commute. That is, if you start from R, suppose you take an element A from R, then from this way you will get a coset A plus car F. Okay. Then you want to define this map phi, so that this phi of A plus car F will go to some element of R dashed. And as part of our definition, we need to have this situation that this A will map to FA. So our intention is to define this phi in such a way that phi of A plus car F is FA. That is, phi of A plus car F is going to be equal to this. So this is our definition of phi. So actually we define, so phi is a map from R by car F to R dashed by the rule that is phi of A plus car F is equal to FA. So this is the map we can define using F and the canonical homomorphism psi. So here you see that phi compose psi is F. Right. Now we need to check that this phi is a ring homomorphism. So suppose you take A plus car F plus B plus car F, then it is actually phi of A plus B plus car F, and this is going to be A plus AB, and so it is Fa plus Fb because F is a ring homomorphism. So therefore it is true that, so it is phi of A plus car F plus phi of B plus car F. And in a similar way you can also check that phi of A plus car F product with B plus car F is going to be equal to phi of A plus car F dot phi of B plus car F. So with this one you can, with these two deduction, you can say that phi is a ring homomorphism. Okay, and by definition phi is onto. Why? As because if we let that some B belongs to R dashed, then using the ontoness of F there exists A belongs to R, so that B is equal to Fa, but Fa will be equal to phi of A car F, A plus car F. So this means that this phi is onto by definition, and it remains to check that phi is 1, 1. So suppose you take two cosets A plus car F and A dash plus car F, and suppose we assume that the images are same. So therefore it is f of A equal to f of A dashed. So that means if A dashed inverse Fa Fa dash minus Fa equal to 0, so this is true. So therefore A dash minus A belongs to kernel of F. Okay, so therefore A plus car F equal to A dash plus car F. So hence the members are same. So therefore phi is 1, 1. So this proves that phi is an isomorphism from R by car F onto R dashed. So that is R by car F is isomorphic to R dashed. So therefore every homomorphic image of R is equal to the quotient of R with some ideal of R. Okay. And the note is that can make a note out of this theorem is that the map we have defined above, that is phi, so this map, this is unique 1-1 map such that phi compose psi equal to F. Okay, so this phi, it must be unique with respect to this condition. Okay, but why? Because if you take another map, suppose you take phi dashed. Okay, so phi dashed is a map from R by kernel of F to R dashed. Be another map such that phi dashed compose psi equal to F. Okay, but then we see that if you take any element from the ring R, then you will see that phi compose psi of A equal to, it is Fa. Now Fa is equal to this one, so it is phi dashed compose psi of A, and that means phi of psi A equal to phi dashed of psi A, that is phi of A plus card F equal to phi dashed of A plus card F. But phi and phi dashed are both are maps, are functions from R by card F to R dashed. So therefore this is true for all R belongs to R, so hence these two maps are same, since their images are same. Okay, so therefore what we have defined above, the map phi is unique one-on-one map with respect to this condition. Okay, and from this theorem you can have two corollaries which are also very important in the theory of rings. The first corollary should be second isomorphism theorem. For rings, second isomorphism theorem for rings. Okay. So what is the statement? In that case also, what we have witnessed in the group theory of groups, the second isomorphism theorem for groups, the same, the analogous statement will hold here, but with respect to the keeping in mind the binary compositions of rings. Okay, so suppose you take a ring R and suppose I be a subring. You do not need to take this as an ideal. Okay, you just consider I to be a subring, but you need to consider one ideal. So be an ideal of R. So J be an ideal of R, but I be a subring. Then you can prove that the conclusion is that I plus J quotient with J will be isomorphic to the quotient ring I modulo I intersection J. Now I have already proved that intersection of two ideals is again an ideal. So therefore here this I intersection J is an ideal, and so you can talk of this quotient ring. Okay, and again since J is an ideal of R, and then you can check that this J will be an ideal of this one. So therefore you can talk of this quotient ring also, and our intention is to show that these two quotient rings are isomorphic by the help of first isomorphism theorem. So we are going to use the first isomorphism theorem. So the statement of first isomorphism theorem is like that. Suppose you take a ring homomorphism from R on to R dash, then R by car F is going to be isomorphic to R dash. This is the conclusion. So firstly you need to consider the specific rings, and then in between these rings you need to define a ring homomorphism F. Then you can use the conclusion of first isomorphism theorem. So here firstly we need to check that whether this I plus j is a subring of R or not. Okay, so our first fact is that we need to prove the first fact, that is I plus j is a subring of R. Why it is a subring? Now since I is a subring, j is an ideal, so here you have the 0 element. Okay, so 0 belongs to I plus j, right? Now to check whether this is going to be a subring of R, you need to take two elements from I plus j. Suppose one is I1 plus j1 and another one is I2 plus j2, which are sitting inside I plus j. Then what is the condition to make this I plus j a subring? You need to evaluate this difference, and which is easily shown to be I1 minus I2 plus j1 minus j2. Okay, now since I is a subring and j being an ideal, in particularly it is also a subring, so this means this I1 minus I2 is in I and this j1 minus j2 is in j, so this belongs to I plus j. Okay, and also if you take the multiplication of these two elements, then you can see that this is I1 I2 plus I1 j2 plus j1 I2 plus j1 j2. Okay, right? So therefore this element will lie in I, because I is a subring. Now using the assumption of j, which is j is an ideal of R, so therefore this j2 is in j and I1 is a member of the ring, so this I1 j2 is in j. Similarly j1 is in j, I2 is in the ring, so j1 I2 is also in j, and here also this is in j. So therefore you can add these three elements and you will get an element of j. So this element is in j, so therefore this element belongs to I plus j, and this proves that I plus j is subring. Okay, now we are planning to define a ring homomorphism from this ring to this one. So here your R is I plus j and your R dash is I by I intersection j. Okay, so define phi from I plus j to I by I intersection j. Okay, by phi of phi of I plus j equal to I plus I intersection j. Okay. Okay. Then we need to check these facts. The first is phi needs to be a ring homomorphism, right? So phi is a ring homomorphism. Why it is so? Because if you take any two elements from I plus j, suppose one is I1 plus j1 and another one is I2 plus j2, then you can add these two and you will get an element like this. Okay, and then it is I1 plus I2 plus I intersection j. Okay, and therefore you will have I1 plus I intersection j plus I2 plus I intersection j. So it is phi of I1 plus j1 plus it is phi of I2 plus j2. In a similar way, if you take the product, so I1 plus j1 dot I2 plus j2, then you will get, so it is phi of I1 plus I2 plus some element of j. Some element of j, as like we have deduced here. So this is an element of I and this is an element of j. So you just write it down as, suppose, small j. Okay. So then it is actually I1 plus I2, sorry, I1 I2 plus I intersection j. So it is I1 plus I intersection j dot I2 plus I intersection j. So hence it is phi of I1 plus j1 and it is phi of I2 plus j2. So therefore this proves the fact that phi is a ring homomorphism. Okay. Now we need to show that this map is onto. So for this you need to take one element from this ring. So what is that? So let I plus I intersection j be an element of I by this. Then it is obvious that phi of I, so phi of I is actually phi of I plus 0, because 0 is in j, so it is going to be I plus I intersection j. So by default phi is onto, right? So hence this map phi is a ring homomorphism from I plus j onto I by I intersection j. Now here you can apply first isomorphism theorem to get, so using first isomorphism theorem to get I plus j by kernel of phi is going to be isomorphic to I by I intersection j. Now you need to evaluate this kernel of phi. What is that? So this is I plus j such that phi of I plus j will be the 0 of this one. So what is the 0 of this ring? This is I intersection j. Okay. So that means set of all I plus j belongs to I plus j such that so what is phi of I plus j? This is actually I plus I intersection j, and which is going to be equal to I intersection j. So that means set of all these elements I plus j such that this I will be in I intersection j. So here this j is in capital J and this I is also in j. So if you add these two, then this is an element of j only, right? So here you got j. So hence I plus j by j is isomorphic to I by. So this proves the second isomorphism theorem. So this is our first corollary of first isomorphism theorem, and now we are going to deduce another corollary which is called third isomorphism theorem for rings. And here too you will witness the same, the analogous statements for rings as that of the case for groups. That is, R be a ring and you consider two ideals in R such that this j should be included in I. Then our conclusion is that the quotient ring of the ring R by j modulo I by j is isomorphic to R by I. Okay. Now note that now since j is an ideal contained in I, so therefore I by j will be an ideal in R by j. An ideal in R by j. Okay, because you can prove that any ideal T of R by j will be of the form I by j, where I be an ideal of R containing j. Okay, so therefore I by j will be an ideal in R by j. So therefore you can talk of this quotient ring. So now again we need to use the first isomorphism theorem. To use the first isomorphism theorem, you need to set up our rings. That is, what would be our R? This is what is your ring R, what is your ring R dashed, and what is your ring homomorphism F. So here we just take this ring R by j and R by I, and phi will be a map from this to this by phi of a plus j equal to a plus I. Okay. Okay. So we need to check this fact that phi j is ring homomorphism. So therefore you can take two elements from r by j, that is a plus j b plus j, then you will see that this is phi of a plus b plus j, and this is a plus b plus I. So this is a plus I plus b plus I. So this is equal to phi of a plus j plus phi of b plus, sorry, a plus I is phi of this. And in a similar way, if you consider the multiplication, so you will get the same thing. It will preserve the multiplication also. Okay. So this is a ring homomorphism, and note that phi on 2 by definition, because if you take any a plus I, then this a is in R, so you can consider this coset a plus j. So by definition phi is on 2, and now you can apply the first isomorphism theorem. So using to get, so R by j by kernel of phi is isomorphic to R by I. Okay. So what is the kernel of phi? You can deduce this kernel. It will be the set of all those a plus j belongs to R by j, such that phi of a plus j equal to the 0 of this, that is I. So this means that a plus j, set of all those a plus j such that a plus I equal to I. So that means this a plus j such that a belongs to I. So you are going to take these elements a from I. So therefore this is actually the quotient ring I by j. So hence R by j by I by j is isomorphic to R by I. So this proves our third isomorphism theorem. Yes. Now let us have a look at this problem. Let's suppose you take a map phi from the polynomial ring over the field f to f by phi of fx goes to fa. Okay. Where a belongs to f, be fixed. You just consider one element from the field a, f, which is a, and then with respect to this element, so you can take this map, you can index it by a. So phi. So phi a of fx is fa. Now you need to check whether this phi a is a ring homomorphism or not. দেখো তো চেক করে এটা করা যায় কিনা। চেক ring homomorphism, and find out its kernel. Kernel, what would be the kernel of phi a? It is actually the set of all those polynomials of this polynomial ring such that phi a of fx will be the 0 of f, that is 0. So that means set of all those fx belongs to this, as that fa equal to 0, right? So therefore set of all polynomials whose one root is a. So this is the set of all polynomials whose one root is a. So this means that these polynomials will have a divisor which is x minus a, right? So this is going to be x minus a gx, where gx belongs to fx. So that means this is the ideal generated by this. Okay. Okay. Now the next question is whether these two polynomial ring Zx and Rx are these isomorphic? Are these isomorphic? কে বলতে পারবে? কে বলতে পারবে এই দুটো রিং আইসোমরফিক হবে কিনা?